First of all, it's wonderful to come back here to Natal. This is, last time I came here, this building wasn't yet complete, and it's clear that this is an up-and-coming center and will be very much part of the new discoveries that await us in the 21st century. And I also want to thank the 6 organizers for inviting me here. That's Catherine, Claudine, Gertrude, Sergio, Pasquale, and Sebastian. Thank you for inviting me. So I'm going to tell you about the speculation that we have. This is work I've been doing with Yasha Komijani, who's a very gifted Rutgers postdoc, and with Anna Toth, who's at TU Budapest, and Premi Chandra at Rutgers. And we're trying to explore the possibility that fractionalization and order can come together. Okay? And so this is the outline of my talk as I zip through it. I'll first review our understanding of order and our understanding of fractionalization and what we mean by the idea that the two could come together. I'll motivate this idea from heavy fermions, and I'll show you how our NRG calculations have been used to show that in impurity models we can actually induce order fractionalization. And then I'll end with first attempts at a classification. Okay? So order is implicit in our understanding of condensed matter systems. And it's based on this beautiful idea of Landau's that you can characterize a thermodynamic system by its energy landscape, and that there are, at low temperatures, valleys, degenerate valleys, which the system condenses into, producing a broken symmetry ground state. And in the modern context, this has been brought up to date with Yang's concept of off-diagonal long-range order, which is the notion that if you look at correlation functions, equal time correlation functions, in such a system that breaks its symmetry, that they factorize at long distances. Okay? And this idea avoids actually having to use broken symmetry wave functions for the discussion, and it's part of the way that people, for example, analyze the correlation functions of variational ground states and in Monte Carlo. Okay? So this is part of our framework, but the other side of the story, of course, is fermions. We're very much interested in fermions. One more point, this is a static correlation property. When we come to fermions, electronic matter, most of our understanding of broken symmetry is built around the notion that we bring together pairs of fermions. This is, in the context of magnetism, the idea of Stoner and Hartree-Fock, the idea that you bring together a particle and a whole and you make a triplet state, and that's a magnetization. Okay? But also BCS pairs. Okay? And when you bring together pairs of electrons, you bring together objects, both of which have spin 1/2, and it means the objects you end up with have integer spin. And so half-integer order parameters, although you might imagine that they're allowed within the general context of the Landau scheme, are clearly impossible within the Hartree-Fock BCS paradigm. Okay? So that's order. Now let's talk about fractionalization. Okay? Fractionalization is something that happens to bosonic operators. Okay? Magnons, in one dimension, fractionalize into spins. In the spin-1/2 Heisenberg model, this is what happens. A spin flip creates 2 spin-ons. They propagate out and they produce this beautiful continuum of excitations in the dynamical spin correlation function that you can measure and you can calculate, and everything squares together. Okay? And so what happens here is that the spin operator actually splits up into separate components, which we can heuristically think of as a product of 2 operators. And this phenomenon occurs in many systems, not just in one dimension. It occurs in the 2-dimensional Kitaev honeycomb model. It also occurs, although it's not so well understood, so well appreciated, in Kondo lattice models, and it may be a feature of something called deconfined criticality. Okay. Operator fractionalization is then, first of all, an excited state property. You see it in the correlation functions at finite frequency, which means these are correlations at finite time. And so it's a dynamic property. These are the 2 contrasting ideas of modern condensed matter physics. Okay? The question I want to ask, and with my collaborators, is whether these 2 things can ever come together, whether you can have order and fractionalization at the same time. In other words, whether an operator can be both ordered and fractionalized into order parameters. Okay? And this is just a conjecture. Can it occur? If order fractionalizes, then this would require, because fractionalization is an excited state property, it'll mean an extension of off-diagonal long-range order into space-time. Secondly, if it occurs, you can now separate out an integer spin object into a product of half-integer objects. And so if it can occur, it means that we will have a new column of order parameters. Half-integer order parameters will become possible. So that's a conjecture. It's on the table, and it could well be wrong. In fact, it's probably got a 99% chance of being wrong. But that 1% leftover chance, if it's true, would be tremendous, and that's why we're interested in it. Okay? Right. So, part of our motivation comes from the Kondo lattice, and I've had lots of interesting discussions at the Flatiron Institute in New York City, and part of that is that we've agreed with talking with Andy Millis that we should think of the Kondo lattice as a kind of Platonic model of theoretical physics. It's an idealization, okay? It's a very old model. It's older than the Hubbard model. It was first written down in 1952 by Kasuya in his thesis, okay? And we're still discovering its properties. Here's a picture of the Kondo problem. And I like to think of it as a many-body ionization. You drop a spin into a conduction C, and that spin then delocalizes as a charge-heavy fermion. If you do that in a lattice, you drop a lattice of local moments into a conduction C, and this highly magnetically polarizable medium melts those local moments, delocalizes them as a band of heavy electrons. And so there are two different views of this phenomena. The old-fashioned view is that the F electron is just the renormalized quasiparticle of the underlying Anderson model. An Anderson model, when you integrate out the charge fluctuations, gives rise to a Kondo model, and remarkably, the two predict the same physics. That's great, okay? But if you give your computer a Kondo lattice model and say, computer, solve that model, it doesn't know that it came from an Anderson model. In fact, those spins could be nuclear spins, okay? And the same physics occurs, okay? So viewed from the perspective of the Kondo model, F electron is emergent fractionalization of the spin as a charged Dirac particle, okay? And we know this is true. We have strong foundations for this. This is a small Fermi surface. This is a large Fermi surface. And what happens in the Kondo lattice is that Fermi surface expands to incorporate the fractionalized spins. And there's a beautiful theorem due to Oshikawa which proves that if there is a Fermi liquid ground state, then the increase in the volume of the Fermi surface is determined by 2s mod 2. Okay? And so, if we look at this beautiful experiment, we can interpret the change in the Fermi surface of cerium, rhodium, indium-5 under pressure as a pressure-driven fractionalization. But this then raises the question, well, what other kinds of fractionalization are possible? Okay? Right? We know that spins fractionalize in a 2D spin liquid. And there's a lot of interest in the Kitaev honeycomb system, which is really realized in systems such as ruthenium chloride. Okay? In that case, the spins fractionalize into Majorana fermions. Well, what would happen if you could initiate a Kondo effect with such a system? Okay? Yes? Oh, wrong address. Thank you. Sorry. My mistake. Okay. Here's one system which is very interesting, uranium ruthenium to silicon 2, which exhibits Ising quasiparticles. And the spin zeros, the multiple spin zeros, tell us that the magnetic field only couples to the Z component, the spins of these systems. And one way in which this might occur is if the quasiparticles are in essence integer spin objects. And so that was the basis of our static theory for heavy fermion, for uranium ruthenium to silicon 2. That's just one motivation. Here's another motivation for you. This is neptunium, palladium 5, aluminum 2. It is the exact counterpoint to materials design. This material was discovered by accident by Dai Aoki when he put neptunium into a palladium crucible, okay, with an aluminum melt. It all interacted and produced marvelous, you can see what it is. It's a Curie magnetic system, a Curie paramagnet, it goes directly from a Curie law paramagnet into a D-wave superconductor. Right? And what happens is these local moments quench. They disappear as it goes superconducting. So in this system, the spin fractionalization, the Kondo effect, occurs with the superconductivity. So sometimes spin fractionalization appears to coincide with a phase transition. Okay? And so the Kondo effect and the superconductivity coincide. Okay? So putting these various examples together, it raises the interest, it really motivates the question, can order fractionalize? Okay? Okay. So let's go back and talk about how this might manifest itself in the self-energy. The self-energy is fundamental in electronic systems. It is this object that determines the many-body physics. Okay? And conventional broken symmetry is local in time. It provides a vice field for scattering the electrons. Okay? Let's look at what would happen. And furthermore, it's an irreducible representation of the group. Order fractionalization would then mean that the self-energy splits up. It factorizes. Okay? And if it factorizes into two independent quantities, this would require that you can separate them out very far in time, which requires, in the fermionic channel, something that propagates without dependence on time, a singular fermion. Moreover, it would mean that this self-energy would no longer be irreducible. It would be a reducible product representation. Okay? And the thing that propagates in between would then have to be a composite fermion. Okay? So order fractionalization, if it occurs, is linked to the formation of fermionic bound states. Okay? This is an idea which we are not alone in being fascinated by. And in fact, the group of Imada, collaborating with Sakai and Civelli, have called such singular fermions dark fermions. And they can see them emerging in their dynamical cluster calculations on the Hubbard model. And here is something from one of their papers showing these poles in the anomalous self-energy. Okay. So, in fact, this is something I'll come back to, but the basic idea then is if this works, it means that three-body bound states, which carry some kind of set of quantum numbers, labeled by this capital lambda, split up into two components, one of which is carried by the order parameter, and the other which is carried by the dark fermion, which propagates away. Okay, so all of that is, I'm sure you agree, sounds like a very nice fantasy. Okay, how can we check it? So we take our inspiration from Curie and Weiss. Curie and Weiss, remember, Curie told us that if you apply a magnetic field to a local moment, you induce a magnetic polarization. You induce a broken symmetry. Okay? And Weiss told us that because of the feedback, you can take that magnetic field away and the broken symmetry will remain. And that is then spontaneous broken symmetry. Okay? So the question is, can we do any of this in an unbiased way? Okay? And a prerequisite is then that we need to establish an example, such as an impurity model, like a local moment, where we can induce order fractionalization with an external field. Okay? Right? Okay. And the Kondo model is a great starting point, because this model has fractionalization sitting inside it. Okay? And we can show it with NRG. In fact, it's already really known. We know there's an Abrikosov-Soule resonance. Okay? That Abrikosov-Soule resonance is the injection of a fermion into the Fermi sea. Okay? The irreducible self-energy of the electrons contains a sharp pole, and multiple scattering of that sharp pole produces the Abrikosov-Soule resonance. We know this from mean field theory, from Nozier's local Fermi liquid theory, but interestingly enough, when you look at DMFT calculations, they usually only show the T matrix with the Abrikosov-Soule resonance. They don't show the sharp pole that is surely there. So one of the things you can do is check it's there. Warm up with a nice NRG calculation and check if it really happens at spin 1/2. And here's the calculation that comes out of that, okay? You see this sharp composite fermion pole, and this background here comes from the omega squared scattering of the emergent Fermi liquid, okay? Nothing very new here, but it is interesting if you think about what's going on inside the self-energy, because what it means is that the irreducible T matrix has a sharp pole in it. You can see the pole here. This is an unbiased numerical calculation showing the sharp pole, okay? Right? And so this sharp pole tells us that the composite of the spin and the fermion combine into a composite fermion, okay? It's a three-body bound state. And this three-body bound state is the origin of this claim that there is hybridization in this system. The hybridization doesn't come from an Anderson model. This is not an Anderson model. It comes from the formation of a composite three-body bound state. And in fact, the hybridization from the point of view of field theory is a Higgs field. And it's a Higgs field for the spin-on, which absorbs the spin-on's U1 field into the electromagnetic field, giving the F electron charge. So it's a little bit different to the kind of fractionalization you see in a U1 spin liquid, because it's Higgs. Okay? So there's no artificial light in this system. Okay, so going on to the two-channel Kondo model, here we have two channels interacting with a local moment, and if it's perfectly symmetric, it's a beautiful example of a critical non-Fermi liquid. Okay? There's a system with an infinite entanglement length, a residual entropy. But if you twink it, if you change the model by adding a little bit of asymmetry in the channels, then you can, of course, induce a Fermi liquid in one channel. And so this good old sharp composite fermion forms in one channel. Fractionalization is induced. Okay? And you can see that again in the NRG. Here's the NRG for the case of the balanced critical non-Fermi liquid. There's no pole in the self-energy. Make the asymmetry in, there it is. Okay? And so what we've essentially proved is that the self-energy picks up this pole. And the pole only occurs in one channel, and therefore it's factorized like this. Okay? We can turn the channel around. We can change its direction by changing the direction in which we apply the symmetry breaking field. But the important point is that this system now exhibits induced off-diagonal long-range order in time. Okay? Now, the composite fermion occurs in one channel. And so you can see that the channel quantum number has been acquired by this spin-on. By this spinner. It's a fractionalization of the composite into a fermion and a spinor order parameter. Okay? So, of course, that's just a proof that we can induce it. Does it occur in a lattice? Well, that's a question of whether there's a Weiss field, and there are a lot of subtleties that can occur in a lattice, but the basic idea would be that now it occurs spontaneously. If it occurs spontaneously, that'll then mean that you have a spontaneous off-diagonal long-range order in space-time of the self-energy. This propagator here is the propagator of the emergent fermions that propagate within the system. Okay? We can study this in various ways. Let me mention that this kind of order is connected with the formation of a composite order parameter, which itself fractionalizes. Okay? This kind of order has been seen using dynamical mean field theory, and here's the nice work of Hisono et al., showing the fact that you get a Kondo insulator in one channel, the channel that hybridizes, and you get a metal in the other. Okay? This system can be thought of as a spinorial magnet, which of course has three Euler angles, in which one of them has become Higgsed by the Kondo effect, to become gapped, leaving behind two magnetic Goldstone modes, okay? Leaving behind a CP2 spinor, which is the order parameter, okay? So I'm basically done, but let me just show you our efforts to try and generalize this. So this example is an example of the composite fermion factorizes into a Dirac fermion and a spinor order parameter. And the composite that's formed, which fractionalizes, is a composite multipole. It's really this channel magnetization. Okay? There are other examples which fascinate us. If uranium ruthenium 2 silicon 2 is an example of fractionalized order, then the multipoles that we're seeking, we heard a very nice example idea yesterday about maybe the multipole being from the group 126. So that would then describe the symmetry of the self-energy. But that self-energy might itself fractionalize into an intermediate fermion, which is the spin 1 or the integer spin fermion that gives rise to the Ising properties. Okay? If that occurs, and in our static theory of this order, this is basically a fractionalization of the self-energy into two hybridizations and a propagator. That would be, that's the static idea. Okay, there are other possibilities. Here's neptunium, palladium 5, aluminum 2. If that's an example of fractionalized order, then, in fact, at one level, there is a composite pair that must form. But this composite pair seems, at least in mean field theory, to be a fractionalized order parameter. And it's a fractionalization of the hybridization in two competing channels for scaling in this particular theory here. If that were to occur, then that's another entry in this in which the composite pairing actually decomposes into a two-component term, one in which you get an electron and one in which you get a hole. This then produces composite pairing. Okay. And last but not, here's another example, the 1,220 materials. These systems are miniature versions of uranium beryllium-13, and they seem to develop novel superconductivity around a quantum critical point, and they are also two-channel Kondo systems. Okay. Last and not least, my favorite one, samarium hexaboride. We had some good discussions about this the other day, and according to these beautiful data here on this floating zone sample of samarium hexaboride, floating zone samples don't contain aluminium, you can see all of these marvelous high frequency and low frequency de Haas-van Alphen oscillations in a system that's a robust insulator. This could be something interesting. This could be a system in which the spin has fractionalized as a Majorana fermion. When the spin fractionalizes as a Dirac fermion, it has enough components to hybridize with a conduction C. But if it fractionalizes as a Majorana fermion, it can only hybridize with 3/4 of the conduction C, and the remaining one propagates as a Majorana fermion, a Majorana D electron. And that's the picture of this system. In fact, this is a picture taken from a paper we wrote before we knew about these things, a paper written with Eduardo Miranda and Alexei Svelik in 1992. Okay, so that basically wraps up my talk. Here are the conclusions. First, the Kondo effect is a hitherto unrecognized form of spin fractionalization. Okay? It's been under our nose all these years, but it really does occur and give rise to an expanded Fermi surface, a system which just has neutral spins. Okay? To understand it, you have to say the spin fractionalized. Okay? Okay? Other forms of spin fractionalization are possible, and they might occur in heavy electron systems. And one way in which this might occur is in samarium hexaboride. It might be a Majorana fractionalization, CF Kitaev. Okay? Simultaneous development of Kondo and order at the same time suggests order fractionalization. The idea that fractionalization drives broken symmetry. Okay? And order fractionalization can be induced in the two-channel Kondo model. We suspect it's stable in the lattice, but we can't prove that, hence the conjecture. Okay? And this is the order fractionalization conjecture in a general form. The idea is that three fermion combinations, which have the quantum number given by this large capital lambda, can factorize into two parts. Okay, a residual dark fermion, okay, and this fractional order parameter which accompanies it. That's the end of my talk. Thank you. We have 10 minutes for questions. 6 minutes, 4 seconds. Okay.